So for this week, we are looking at Chapter 11, comparing two populations or two treatments within the same population. So for example, suppose we have a population of adult men with a height of 71 inches and a standard deviation of 2 inches. We also have a population of adult women with a mean height of 65 and a standard deviation of 2.3, assuming that the sets of heights are normally distributed. Suppose we take a random sample of 30 men and a random sample of 25 women from their respective populations and calculate the difference in their heights. So the man's height minus the woman's height. If we did this many times, what would the distribution of the differences look like? So both populations are normally distributed, so they have that bell curve. The differences would also, of course, the normally distributed. So we have the sampling distribution for a sample size of 30. This is the male heights for individual heights. This is the distribution of the sample means for samples of size n equals 30. And so the same would be true for the women. Their sampling distribution would also be a curve narrower than the others. Of course, that sample size of 25 there is what we're taking for the women. So if we are subtracting the mean of the sample for men and subtracting then the mean of the sample of women from that, we're going to get a bell curve. So it's still normally distributed. And the standard deviation of that is going to be a combination of the standard deviations for each of these regular distributions. Notice it's the standard deviation divided by the square root of the size of the sample squared, and then we add those and take the square root. It's what we refer to as a Pythagorean relationship. We square them and then square root. So let's describe the sampling distribution of the difference in men's heights between men and women, in heights and mean heights between men and women, I should say. So the sampling distribution is normally distributed. The mean is just the difference between the means. 71 minus 65 is 6. The standard deviation of that distribution of the differences is, again, the combination of the two standard deviations, the square root of the men's standard deviation squared divided by the sample size, plus the women's standard deviation squared divided by the sample size. What is the probability the difference in mean heights of a random sample of 30 men and 25 women is less than 5 inches? Well, this is just going to be a normal distribution. Mean of 6, standard deviation of that, whatever that number comes out to be. And it ends up being a probability of 0.0614. So the properties of the sampling distribution of the difference of two population means. So the random samples on which x1 and x2 bar are based on are selected independently of each other. So that's very important. The two random samples have to come from independent populations, so no crossover in the populations, and have to be selected independently from each other. So the mean of the difference of the means is going to be equal to the difference of the population means. The standard deviation for the difference in the means, again, is going to be found by taking the sum of the two standard deviations of the population squared, which gives us this little formula here for combining those standard deviations. So the variance of the differences is just the sum of the different variances. Now, in the N1 and if N1 and N2 are both large, or the population distributions are approximately normal, X1 bar and X2 each have at least approximately normal distributions. This implies that the sampling distribution of the difference of those means is also approximately normal. The properties for the sampling distribution of X1 minus X2 bar implies, the bars got screwed there, X1 minus 2 can be standardized to obtain variables with a standard distribution. In other words, we can apply standard normal probabilities to these once we calculate that mean and that standard deviation. So when two samples are independently selected from both large or normally distributed populations, the distribution is normal. And we can standardize it using a z-score. And then we can use that z-score to find probabilities if we would like. Now, the catch is we must know both of the population standard deviations in order for that to work. If they are unknown, then we have to use a t-distribution to approximate those probabilities. So a two-sample t-test for comparing two populations. Let's say our null hypothesis is that the two populations are the same. In other words, mu1 minus mu2 equals some hypothesized value. Usually we use 0 for that hypothesized value. So if it is 0, then we can reword those hypotheses a little bit different. We'll see that coming up. So our test statistic is the difference between the sample means minus whatever the hypothesized value of the difference is, again, usually 0, divided by that combined standard deviation. So the appropriate degrees of freedom for a two-sample t-test. This is going to be a little tricky finding the number of degrees of freedom. So the degrees of freedom, v1 plus v2 squared over v1 squared over n minus 1 plus v2 squared over n minus 2, n2 minus 1, where v1 is simply s1 squared over n1 and v2 is s2 squared over n2. In other words, it's the standard deviation of sample 1 squared divided by the size of sample 1. And v2 is the standard deviation of sample 2 squared divided by the size of sample 2. The computed number of degrees of freedom should be truncated to an integer. So even if it is like 27.9, it gets rounded down to 27. Truncated means always rounded down, never rounded up. So, and this ends up giving a conservative estimate of the p-value using this number of degrees of freedom on the curve. So let's do a two-sample t-test for comparing two populations. Our null hypothesis is that the difference of the means is a hypothesized value. The alternatives is that difference of the means is larger than the hypothesized value, or the difference of the means is smaller. This would be the left-tailed test, or simply that the difference of the means is different, not equal to. So this would be a two-tailed test. So when the hypothesized value of the difference is 0, we can simplify our hypotheses. The null hypothesis can just be that the two means are equal. And then the alternative, rather than being that the difference is less than 0, we can just say mu1 is less than mu2. Rather than saying the difference is greater than 0, we can say mu1 is greater than mu2. Or we can simply say that mu1 is not equal to mu2. But we have to make sure we define both mu1 and mu2 here. We can't just compare one of them to a number. So some assumptions that are needed to make sure that we can do a t-test. Two samples have to be independently selected random samples from independent populations. Sample sizes are large, either 30 or larger, or the populations are approximately normally distributed. When we compare the two treatment groups, we use the following assumptions. The individuals are randomly assigned to the treatments, and the population sizes are large again, or the treatments are approximately normally distributed. So in this example, are women still paid less than men for comparable work? Study carried out in which salary data was collected from a random sample of men and from a random sample of women who worked as purchasing managers and who were subscribers to Purchasing Magazine. Annual salaries in thousands of dollars appear below. The actual sample sizes were much larger. So we just took a random sample out of their samples here. Using alpha of 0.05, determine if there is a convincing evidence that the mean annual salaries for male purchasing managers is greater than the mean annual salaries for female purchasing managers. Now, before we perform this test, I should give a side note here. One thing that, using these simple tests, we can't take into account all factors. One thing that's not taken into account here is years on the job. Somebody has been at their job for 8 years, you would expect them to be making more than someone who's in their job for 3 years. Or the size of the company they're working for. Working for a larger company, probably a little bit more responsibility, you would expect them to be getting paid more than someone working for a very small company. So this is only taking into account salaries, not other factors that might contribute to those salaries. So our hypothesis. The null hypothesis is that the difference equals 0. The alternative is we are claiming that men make more than women. So mu1 is minus mu2 is greater than 0. So mu1 is the mean of the male purchasing managers. If we had defined it as the female purchasing managers, then we would have to switch this around. So mu2 is the female. Again, if we had defined those to be the male, that would totally change the way we did this. So the salary award here for our hypothesis test. So mu1 is the mean salary for males, mu2 is the mean salary for females. We verify our assumptions. Sample sizes are small, but they are independently selected from each of the populations. And since they are small, we do the little box plots, and from the box plots we can see neither one of them is severely skewed or has any outliers, so they are approximately normal. Now let's compute this test statistic. The test statistic here, the difference in the mean. So we found the mean for each set. The mean of the group of males is 74.6. The group of females is 64.6. So we subtract those to get a mean difference. Then we subtract the hypothesized value of 0 from that. The standard deviation for men was 5.4 and for women was 8.6. So we combine those. We get a test statistic of 3.11. Let's find the p-value of that. So the p-value, we need to find the degrees of freedom. So we combine. Remember, this is the 5.9 here is that V1. That V1 is found by taking standard deviation 1 squared and dividing it by the sample size. So basically, this value right here, that is V1, and this value right here is V2. So that's where these each came from. And we get 15.14. Again, we truncate that, which means we always round it down to 15 degrees of freedom. So we are looking up this probability of being, this is greater than here is our alternative. So we want to find the probability of T being greater than 3.11 with 15 degrees of freedom. And we get a p-value of 0.004. So that is less than alpha of 0.05. So we would reject HO and say that this sample does seem to indicate that there is a difference, that men are paid more than women in that field. So now, since we rejected the null hypothesis, it is possible that we made a type 1 error. The probability that we made that error, of course, is that p-value. So that probability that error is pretty small here. So a two-sample T confidence interval for the difference between the two population means. So independently selected random samples. Samples are either large or the populations are normal. We have the difference in the two sample means, plus or minus the critical value times that standard error, standard deviation again, that combined value. So again, we have to find our degrees of freedom using that same formula we did before. Again, truncated to the nearest integer, lowest integer. Again, make sure that we use these assumptions are the same assumptions we used for hypothesis testing. So in a study on food intake after sleep deprivation, men were randomly assigned to one of two treatment groups. The experimental group were required to sleep only 4 hours on each of 2 nights, while the control group were required to sleep 8 hours on each of the 2 nights. The amount of food intake in kilocalories on the day following the 2 nights of sleep was measured. Compute the 95% confidence interval for the true difference in the food intake for the 2 sleeping conditions. Now again, here you might take the size of the individual. Someone who is larger obviously is going to take in more food just because of calorie requirements, or more active. Physical activity could have a huge effect here. That's not taken into account. All that's being taken into account here is hours of sleep compared to food intake or calorie intake. There's a lot of things left kind of out in the gray here. So I found the mean for the 4 hours of sleep and the standard deviation for the 4 hours of sleep. That's the calorie intake. Then the mean calorie intake for 8 hours of sleep and the standard deviation for those. Now, surprisingly, the 8 hours of sleep seems to be larger. So we verify our assumptions. Those are independent samples from 2 different treatments. The box plots seem to indicate that they are both normally distributed. We calculate our interval. So the difference in calories, right there, that is our T critical for our degrees of freedom. That is our combining of the standard deviations from the 2 sets to get a combined standard error for the differences, giving us that interval, negative 814 to 523. Now, since that interval contains 0, we cannot conclude that there's any differences here. So we're 95% confident that the true difference is in that interval. And based on the interval, there isn't a significant difference between the 2 conditions, because that interval contains the value of 0, which means it's possible that the true value is 0. A pooled t-test. You can use a pooled t-test when the variance of the 2 populations is approximately equal. It combines information from both samples to create a pooled estimate of the common variance, which is used in place of the 2 sample standard deviations. So it is not widely used due to the sensitivity. Even though the variances may be really close to equal, if they're even slightly different, it can really affect your results. So it's not used very often. The pooled variance for the pooled t-test was used to drastically simplify the calculation. Now with electronic means to assist us in those calculations, it's really not as necessary as it used to be. So p-values computed using a pooled t procedure can be far from the actual p-value if the variances are not really equal. Even if they're slightly different, it can be far off. So suppose that an investigator wants to determine if regular aerobic exercise improves blood pressure. Random sample of people who jog regularly and a second random sample of people who do not exercise regularly are selected independently from one another. We can conclude that the difference in mean blood pressure is attributed to jogging. Well, not necessarily. There may be other lifestyle differences. People who jog more may get more sleep, may sleep better, or they may have a better diet. They may be more health conscious in general. Who knows? Other factors like weight. Again, joggers tend to have lower weight. Really hard on the body to jog if you're overweight like I am. All sorts of things that come into play there. So one way to avoid these difficulties would be to pair subjects by weight and then assign them one to jogging and one to no exercise. That would be called a paired test. So you have to have some sort of common characteristic. In this case, it would be similar weight that they're pairing them together. I would say that also similar weight and probably similar initial resting blood pressure would be things I would consider when doing that. So now our test statistic is not the difference between two sample means, it is the mean of those differences. Our data point is not the individual data points, but it's going to be the difference between the readings for the two members of the pair. So the hypothesized value is usually 0 again, meaning that there is no difference. Our test statistic is just the mean of the differences minus that hypothesized value divided by the standard deviation of the differences divided by the square root of n. Now, since we're using this differences as a data set, there is no population to go to there. So it can't be a z-test because we don't have population values. So a paired test will always be a t-test, and you will always be using the standard deviation of that sample of differences. So n is the number of sample differences we have. X bar d and SD are the mean and standard deviation of the sample of differences. And of course, the degrees of freedom is just the number of differences minus 1. So again, for our p-value, it's going to be the same based on the alternative hypothesis, whether it's a right tail, left tail, or two tail. So the summary, our assumptions, the samples are paired, and there's a good reason for pairing them. It has to be a reason valid to the purpose of the study that we're pairing them. The n sample differences can be viewed as a random sample since the individuals were randomly placed. And the number of sample differences is large. So either we have at least 30 sample differences, which is not very common. Usually a paired test is a lot smaller sample. Or the population distribution of differences is approximately normal. Usually that's the one we go off of. So here's an example. Now, is this an example of a paired test? An engineering associate wants to see if there's a difference in the mean annual salary for electrical engineers and chemical engineers. Random sample of electrical engineers is surveyed about their annual salary. Another sample of chemical engineers is surveyed about their income. This is not paired because we just have two independent random samples. There is no connection between the individual members. We're not looking at subtracting individual members. We're looking at subtracting the means of the whole sample. How about this one? Pharmaceutical company wants to test its new weight loss drug. Before giving the drug to volunteers, company researchers weigh each person. After a month of using the drug, each person's weight is measured again. This is a paired test, even though it's not two samples, it's one sample with two different treatments, a before and after. Can playing chess improve your memory? A study of students who had not previously played chess participated in a program in which they took chess lessons and played chess daily for 9 months. Each student took a memory test before starting the chess program and again at the end of the 9 months. So we have 12 randomly selected students and a before and after, pre-test and post-test. So again, it's not two separate samples, it's one sample with two different treatments. We've got their differences on that test. So the hypotheses is the null hypothesis is that the mean difference is 0. The alternative would be that the mean difference is less than 0. Had we subtracted the other way around, of course, that would change the alternative hypothesis. Here we did pre-test minus post-test, so we're assuming that if their memory improved, those differences would be negative. So then we verify our assumptions. Yes, they are random samples. It was a random sample, and of course they are using the same sample twice with two different treatments. The box plot shows that the differences are approximately normal. Compute the test statistic. Well, the mean of the differences, so the mean of these values here is negative 144.6 minus our hypothesized value of the difference was 0. That's our standard deviation of that set of differences divided by the square root of the sample size, giving us a test statistic of negative 4.56. We have 11 degrees of freedom here because we have 12 pairs, so 12 minus 1 gives us 11 degrees of freedom. P-value is approximately equal to 0. It's extremely small. So that means our p-value is less than alpha. So therefore we reject HO. So there's convincing evidence to suggest that the mean memory score is better after chest training than before. So paired T confidence interval. So we can also do a confidence interval for this rather than just hypothesis test. So again, all the same assumptions apply. It is that mean difference plus or minus the critical value times that standard deviation over the sample size, the standard error. So same values here. We're just arranging them different. So that's our mean of these differences. That's the standard deviation of these differences. That, of course, is a critical value from a t-value with 11 degrees of freedom, giving us an interval from negative 201.5 to a negative 87.69. Again, this is a 90% confidence interval, so we are 90% confident that the true value of the difference is in that range. And since that does not include 0, that confirms that, yes, it does show that there is a change in memory due to chest training. So let's do large sample inferences concerning the difference between two populations or two treatments. So some people seem to think that duct tape can fix anything. It can remove warts and all sorts of other things. So suppose duct tape treatment will successfully remove 50% of warts, that traditional treatment will successfully remove 60% of warts. Does that mean that the traditional treatment is better? Well, let's investigate the difference between the proportion that is fixed by freezing and the proportion that is fixed with duct tape. So P freezing, the true proportion of warts that have been removed by freezing, we're going to use 0.6 as that estimate. And the P for tape, that is the true proportion of warts that are successfully removed by using duct tape, we're going to use 0.5. Each of those separately has a normal distribution. So the normal distribution for the difference of those is also normally distributed, and we're combining the variances similar to the way we combine them for means. So assumptions that need to be made, they're selected independently from each other. The difference in the proportions, the mean of the difference in proportions is just the difference in the proportions. It's an unbiased statistic. And we can combine the standard deviations again, just like that, like we did, just combining the two standard errors from the sampling distributions. And as long as both N1 and N2 are large, that is, N1 times P1 is 10, N1 times 1 minus P1 is 10, N2 times P2 is 10, and so on is at least 10, then we can assume that it's approximately normal. So when we perform a hypothesis test, we'll use the null hypothesis that P1 and P2 are equal. So that's generally what we would use. We will not know the common value for P1 and P2. So since the value for P1 and P2 are unknown, we will combine P1 and P2 to estimate a common value of P1 and P2. That combined value, the P combined, call it P hat, is N1 times P hat 1 plus N2 times P hat 2 over N1 plus N2. So let's take a look at how this works. So our null hypothesis is that the difference in the proportions is 0. The test statistic is found by using that combined proportion. Again, that is that combined PC is combining the two proportions from the samples. The alternative hypothesis p-value is found the same way depending on whether it's right-tailed, left-tailed, or two-tailed. So another way to write the hypothesis statements, again, rather than saying P1 minus P2 is 0, is that as long as that difference is 0, we can just alter that to say P1 equals P2. And the same for the alternatives. Just like before, as long as that difference is 0, rather than looking at the hypothesizing on the difference, we can compare the proportions The summary of the large sample z-test for P1 minus P2. We have to assume they're independently chosen samples and that both sample sizes are large. The n times P is greater than or equal to 10 qualifier still applies. Since P1 and P2 are unknown, we have to use P hat, the sample proportions, to verify, just to verify that they're large enough. So let's take a look at this back to the duct tape investigation here. So we've got liquid nitrogen, freezing, sample size of 100, 60 successfully removed. For duct tape, sample size of 104, 88 were successfully removed. Do these suggest that freezing is less successful than duct tape? Well, those are hypotheses. The assumptions, yes, they were randomly assigned or randomly selected. And the sample sizes are large enough, all the indicators are larger than 10. So our test, we're going to do our pooled proportion. So all we're doing there is taking x1. This is an easier way of doing it rather than the formula from before. This is just x1 plus, do the superscript, I should do a subscript. This here is x1 plus x2. So that's the 60 plus the 88, the successful ones, over n1 plus n2, giving us a 0.73. So that is that combined proportion. And that's what we end up using in our test statistic to find that standard error of the proportion, difference of proportions. So that gives us a test statistic of negative 4.03. Since this is proportions, it's always going to be a z statistic. And then as we use the standard normal or the z distribution, we can find that p-value is approximately 0, which is less than our alpha of 0.01. So we reject the null hypothesis. Duct tape is more effective than freezing, according to these samples. We want to do a confidence interval. Same assumptions have to apply, so you have to meet these qualifications. So that is, again, just rearranging it. So it's the difference of the proportions. The critical value now multiplies that standard error. So in the same, in the article Freedom of What, describes the study of high school students and high school teachers, we're asked whether they agree with the following statement. Students should be allowed to report controversial issues in their student newspapers without the approval of school authorities. It was reported that 58% of students surveyed and 39% of teachers surveyed agreed with that statement. The two samples were 10,000 high school students, 8,000 high school teachers were selected from across the country. Now we needed those numbers because we need to know that those were large enough to meet the assumptions. So we're going to compute the 90% confidence interval. So P1 is students, P2 is teachers. Assume that it is reasonable to regard these two samples as being independently selected and representatives of the population of interest, yes. They are adequate sized. So 0.58 is the proportion for students minus 0.39 proportion for teachers. Plus or minus 1.645 is the critical value for Z on a 90% interval. This is our combined proportions. We get a confidence interval of 0.178 to 0.202. So we are 90% confident that the true difference in proportion is in that range. Also, again, since 0 is not in that range, it seems to indicate that there really is a difference between the proportion of students that believe that and the proportion of teachers. Now, I realize I flew through this quite quickly this week because the actual calculations by hand are not as important. The calculator is there for us. Excel and Minitab are there for us as well. But it's just understanding the procedures and when you can combine and can't combine. I don't recommend doing a lot of these calculations by hand. Okay, with that, that is it for this week. So if you have any questions, please let me know. Otherwise, you guys have a great week.